get into calculating or deriving the expression for the free energy of the disordered diblock solute and our homopolymer solvent to figure out and be able to compare essentially the chemical potential or the change in free energy as we add a single diblock. So again, free energy per diblock for the disordered state. So before we, if we're not in the kind of micelle state. So we are going to use, again, lecture 4, the most important lecture in this entire class, but we're going to describe the free energy of our disordered state. So this is the scenario where we have, let's keep consistent with our expression here. So we have A, and we have B, and we are mixing basically these polymers in this homopolymer solute. So in the disordered state, we're just mixing them together. We're not forming the micelle. So we can describe that the same way we've described our Flory-Huggins theory. So what changes in here? So we know that we're looking at chi A because we know that chi A is equal to 0, which equals to chi B. And we also know here, quick notation because we're looking at block copolymers. So species 1 and 2 are just A and B, but again, there are block copolymer volume fractions. So x sub 1, x sub 2, x sub 1 is going to be equal to Na and B, so it's phi A over Na and phi B over NB, as you can see here. So we know that the degree of polymerization are going to be very large for polymers. So this term and this term is going to be very, very small. So we're going to be able to kind of, again, make the assumption that they are very small, very reasonable assumption, and we could ignore those two terms. So what are we doing here? Again, we're ignoring effectively this delta S of mixing. That's kind of what we're saying by those large and small values here. So the term that we're left with is only our enthalpic term. So the delta G of our disordered state is approximately this NKT. Again, here chi is this chi KB as well. So one thing that we want to look back here, and remember back from Flory-Huggins, back a page, this N naught, where did that come from? Well, N naught was that total number of lattice sites in our imaginary lattice. So we can instead let N naught be equal to N, where N is just the length of our single diblock in the current formalism. So N equals Na plus Nb, again, for a single diblock. So the expression gives us the free energy change for a single molecule. So it is just this energy per N, the length of a single diblock. So multiplying it through, again, that's where we, you could see this expression N. So here in this expression, it's just KT lambda. We make this approximation that N naught equals N. And now we have the free energy per polymer chain. So if we multiply it out, the free energy then is just going to be this NKT. So again, free energy change per polymer, this is equal, approximately equal to the chemical potential, because we know chemical potential equals dG dN. We're going to approximate it. That's just the change in chemical potential, change in adding a single block copolymer N, so single one diblock copolymer DCP, diblock DB. Anyways, diblock copolymer. So that was what we're working with here. So this is our notation. Again, we've just switched from A and B like we've discussed previously, or just a second ago in that video. So this is great, and we have the two volume fractions A and B with basically the volume fraction of our diblock versus what we have to put now. So this is the volume fraction of A, volume fraction of B. But we need to put in the terms of the volume fraction of the diblock versus the volume fraction of our homopolymer. So we know that the total volume fraction of A is going to be homopolymer plus our diblock. And we also know that our volume fraction of B is going to just be the volume fraction of B in our diblock. So we can kind of rewrite, and we want this expression to be in terms of the volume fraction of our diblock. So we know that we're working with this 50-50 mix right here. So we can kind of start to rewrite this expression in terms of the volume fraction of our diblock, in total. So we know if Na equals Nb is equal to N over 2, then our volume fraction of our diblock is just going to equal, or let's keep the notation, our volume fraction of our diblock is just going to be equal to the volume fraction of A plus the volume fraction of B, and thus we know that volume fraction of A of our diblock is going to be equal to B over 2. Because again, this is just the sum of these, and then we know that those are equal. So you can hopefully convince yourself of that. So we're just making in these substitutions here. So homopolymer is going to be everything again. Phi is now our volume fraction of the dye block, so homopolymer is just 1 minus everything else. So here, here, and then we just substitute that in to this expression right here, and we can make one more approximation or assumption. So the volume fraction of the dye block is going to be much of the solute. So our dye block is going to be much smaller than that of the homopolymer solvent. So phi is going to be much less than 1. If phi is much less than 1, then we know that this term here is going to be approximately 1. So this is going to disappear, and then we're just left with this expression right here. And remember, this is the free energy per polymer in our disordered state. So next time, we're going to get into the free energy of our micelle state and look at the different contributions that come into play there. And then we're going to have to work on 3 fairly in-depth derivations from that. So more on that next time. See you in the next video. Bye.